about the imperfection in solid. Yeah? Basically, the complete title of the chapter is Solidification and Imperfection in Solid. So in this chapter, or we will address the issues like solidification mechanism. Solidification mechanism means usually when we make material, we melt first, yeah, the solid material into molten state. After that, we reduce the temperature, we cool it off. So that then, in the liquid state, the atoms are moving quite freely, but then when we cool down, the energy is lowered, then they will start to arrange each other in a crystalline manner, in a crystalline state in most of the solid material. So by carefully controlling the solidification mechanism, then we can also control the material properties. So in this chapter also we will discuss about types of defects arising in the solid. This defect usually occurs during the solidification process. And it is not that easy to have completely defect-free material. And in many cases, we require defects. Of course, with controlled number, with controlled type of the defects. That's why the third issue that we will address in this chapter is, can the number of and type of defects be varied and controlled? How will these defects affect material properties? And are they undesirable? In many cases, they are not really undesirable. It means they are needed. Sometimes or many times they are required to control the properties of the material. For example, if we have a perfectly defect-free material, sometimes maybe it will be too hard and very difficult to form, etc. So then we introduce defects, so that then those hardness can be reduced, for example. Okay, and this occurs with many other materials properties. So what is solidification? Yeah, solidification is the result of casting molten material. So casting means the molten material is being formed in certain cast. Cast is what we call mold, yeah, cast and mold. Cetakan, mold. Yeah. So the mold is usually made from ceramic material, which can withstand very high temperature. So when we put the molten material in cast and mold structure, we cast the material, cor in bahasa Indonesia. There are two steps that will occur. First, nuclei will form. Nuclei is some small core or seed of the solid material. The nuclei will form. This occurs because some of the atoms will, because of the cooling down, then some of the atoms will be close to each other, and they try to arrange to have the smallest and at the minimum energy level, so that they are in equilibrium. It means they are more in equilibrium state. And this nuclei will form, will grow, and then they will, let's say, ask the other atoms to join, if you can say it like that, and then they will grow. They become then grain structure. The number of the nuclei will determine how many grains we have in that particular molten state of material. We can have small number of nuclei. In this case, then we will have small amount of grain. If we want to have single crystalline material, then we should make sure that the process only will make a single nuclei, which will grow into a perfect single crystalline material. But if not, then we will end up with many nuclei, which each will grow, and then until their growth will be stopped by the other grain. Yeah. So this one, the nuclei is like a seed, yeah, in the to solidify. Then the nuclei will grow into crystals until they cannot grow anymore because they met the other crystals and they become grain structure like this. Crystals grow until they meet each other. So in polycrystalline materials, there are these grain boundaries, yeah, which cause the regions between the crystals, like the borders between countries in the world. transition from lattice of one region to that of the other. So because each of the crystal grain usually have different plane. That's why in the previous chapter we see when we impinge and hit one block of crystal with an X-ray, and then that crystal is polycrystalline, that material is polycrystalline, then within that single material we may have different various crystal orientation, which will result in different peaks coming out in the XRD pattern. And the grain boundary is slightly disordered, and we have low density in the grain boundaries, yeah, because it is the space between the different crystals, so they do not have, they are slightly disordered. They have more space, empty spaces, and that's why within in the grain boundaries, you will have high mobility, for example, of carrier like electrons, high diffusivity of gas, of other impurities, as well as high chemical reactivity. For example, like gas sensor. Why gas sensors can detect gas? Some gas sensors works based on the mechanism that the resistance will decrease or increase when it binds certain gases. The gas is basically diffused into these grain boundaries and binds to the surface of the grain boundaries, making reaction with the charge carrier in the grain boundaries, and then you will have lower resistivity or higher resistivity. Okay, so here, for example, we have different grains. So here this orientation, here we have this kind of orientation, here another orientation at this level. So between this grain and this grain, there are only slight difference of orientation. That's why this is the angle of misalignment. This is the boundary. The angle of misalignment between this grain and this grain is small because they are more or less closely oriented toward the same orientation. But between this and this one, yeah, this one orientation is this direction and this direction. Okay, this direction. Well, this one is this direction. You have larger angle, yeah, which means you have high angle grain boundaries. So during the solidification, you put the molten metal into the cast. Then it will start to grow in the cast. So the heat will flow like this from the middle. The middle part will be the hottest part of inside that volume of the cast, and the coolest part will be the one in the boundary with that touch the mold material, yeah, the ceramics, for example, because it is in room temperature. Yeah, that's what the heat, because the heat transport follows the diffusion mechanism. The heat will flow from the middle to the edge. Yeah. So as such, then the crystalline grain will also grow in that direction here. Okay, the grains can be equiax, especially roughly same size in all directions, especially near the border of the cast material here. Yeah, you see that it is more globular shape, but it could also, the grains can grow as columnar grains with elongated grains. Yeah, especially when from the middle towards the direction of the edge of the cast. Okay, so this one is columnar in area with less undercooling. This is more of equiax grains because of the rapid cooling, because they are near the wall. The wall is very cold compared to the molten material. That's why then they have greater temperature difference. Then they they grow as equiax grain. While in the middle, they they grow according to the flow of the heat. So when we want to make a refined grain, we have to make it smaller size, more uniform shape, as well as equiax grains. So now, what about imperfections? We have discussed a little bit. So there is no perfect crystal. There is you don't have very perfect crystal. Like There is no perfect man or person. Everyone has some imperfection in one way or another. Similarly, with crystal, like that. What are these imperfections? Why are these imperfections important? So many of these important properties of materials are because of the presence of those imperfections. That is why it is not that wanted as well if we have a perfect material, because then we cannot adjust its property according to our application. So we can adjust the properties of the material by controlling the presence of the imperfection. There are some types of imperfection based on the geometry. We will discuss both point imperfection or point defects, then line imperfection, then plane imperfection. So point defects includes of vacancy atoms, where there are space in the crystal lattice that is supposed to be filled by atoms, but instead the atom is not there. It could be also point defects could also be in the form of interstitial atoms, where there are other atoms which fills in the gap between the atoms in the crystal lattice. Or substitutional atoms, where the atom is replaced by another impurity coming from outside, replacing the correct atom in that place in the crystal lattice. Then we have line defects in the form of what we call as dislocations. Then we have area defects, the grain boundaries, like pictured in the earlier slide. So let's go now for the point defects. The first point defect type is vacancies. This is if we have vacant atomic sites in a crystal structure. Yeah, there is supposed to be an atom here, right? If you want to have a perfect crystal, ordered crystalline structure. However, due to some or another causes, the atom somehow is missing from this place. Then we have a vacant atomic site. So this vacancy in this atomic structure and this crystalline structure will cause this distortion of planes. So the atoms in the nearby location will tend to fill in this gap in order to minimize the energy in this area. Minimize means then it makes it more stable. Okay. Then we have self-interstitial defects. In this case, we have an extra atom which tries to find its place in the ordered crystal structure, while actually there are no more spaces. So in that case, you just push the surrounding atom to fill that space which is not actually which actually does not belong to it. Yeah. So then it will cause a distortion as well, in order that the whole energy will become minimized. As you see that distortion, however, in the different direction compared to the vacancies. In the vacancies, the distortion of the planes will be directed towards the place where the vacant sites occur, but in the self-interstitial, the distortion of place is directed outward. In the self-interstitial, the atom that fills that extra space, or that extra atom that fills the space, the gap between the other atoms, comes from the same element. That's why it is called self-interstitial. So the concentration of these point defects, we can calculate the equilibrium concentration. The equilibrium means where it reach the minimum energy, so that then the condition is in equilibrium. So it is determined like this: the number of defects, NV, divided by N, the number of potential defect sites. This is equal to the exponent of minus QV over KT. K is Boltzmann Constant, QV is activation energy, T is the temperature. So you see here, if T is larger these terms become smaller, but minus smaller means becomes minus larger. So this value becomes larger. So if T is increased, you have more number of defects, yeah, in a high temperature compared to if your temperature is low. So each lattice site in the crystalline structure is a potential vacancy site. And the number of defects that occur will depend on this. If you have lower activation energy, then you will have more defects because more lower energy barrier in order to create a defect. So the Boltzmann constant is 1.8 times 10 to the power minus 23 joule per atom per Kelvin. So usually, therefore, the QV, the activation energy, is usually obtained from experiment by putting the material in certain temperature and then detecting the number of the vacancies, yeah, the number of defects that occurs there. The NVNN is basically an exponential dependence towards the temperature. Yeah, as we have mentioned earlier. So the higher the temperature, the hotter the system is, then you have more frequency. You have more defects. Okay, you have more defects in that potential sites. If you put in natural logarithm, and the x-axis become 1 over t, so that it is smaller. And from the slope, then we obtain this minus qv over k constant. So here the both sides you take natural logarithm ln of nv over n, ln exponent minus qv, so ln and exponent cancel each other and become minus qv over k. So the x-axis you draw the 1 over t parameter. The y-axis is natural logarithm of nv over n. The slope will be minus qv over k. So from here, then you can, since k is a constant, then you can calculate the minus the qv, yeah, the activation energy. Let's say here an example. Find the equilibrium or the number of vacancy is 1 meter cubic of copper at 1000 degrees Celsius. But the temperature is usually always in Kelvin. Yeah. So if density is given 8.4 gram per cubic centimeter, the atomic weight of copper is 63.5 gram per mole. The activation energy is known to be 0.9 electron volt per atom. The Avogadro number is 6.02 times 10 to the power of 23 atoms per mole. So the vacancy concentration we can calculate using the formula NV over N equals exponent minus QV, yeah, divided by KT. So K is known, QV is known, T is also known. So we convert 1000 degrees Celsius to Kelvin. So by adding 273 degrees, so it becomes 1273 Kelvin. From here, we obtain 2.7 times 10 to the power of minus 4 of this ratio. Okay. For 1 meter cubic, the lattice site, yeah, the N representing the vacancy site for 1 meter cubic equals to the rho, the density, time this Avogadro number divided by the atomic weight. So here we obtain, this is gram per kilogram per meter cubic, right? Gram per centimeter cubic. This is gram per mole. We obtain per mole. This is atoms per mole. So the mole cancel each other. We obtain atoms per centimeter cubic. Then times here we have how many atoms per that 1 square meter cubic. And here we obtain 8 times 10 to the power of 28 sites. So if we have the ratio NV to N is 2.7 times 10 to the power minus 4, the NV, the number of vacancy, will be this sites times this ratio. Okay, so then we will have at this temperature, we'll have 2.2 times 10 to the power of 25 vacancies. Quite a lot, yeah? So, but compared to the number of sites, yeah, this is the ratio. It can be considered quite a lot still. So this is how the equilibrium vacancy concentration is being observed. This is using low energy, an example, using low energy electron microscope of 110 nickel aluminum alloy crystal. So increasing the temperature will cause the surface islands of the atoms to grow. This is the surface island. Okay? The island grows or shrinks to maintain equilibrium vacancy concentration in the bulk. When we increase the temperature, more of these atoms go to the surface and make this island. As a result, then the original place of that atom will become vacant. That becomes vacancy here, vacancy defect. The equilibrium vacancy concentration increases via atom motion from the crystals to the surface. And then at the surface, they join each other to become island. So in order to lower the energy to maintain equilibrium, they make an island. So for example, here, this is from one journal in Nature 2001, formation of island, surface island, in nickel aluminum alloy. Point defects in alloys. In alloys, if you have 2 or more elements type making a single material. Yeah, in the previous example, we only mentioned about point defects for a single type of material. Yeah, the vacancy, interstitial, or substitutional. Then when we have alloy, we can have what we call as impurity added to the host. So solid solution of B, the impurity, in A random distribution of point in the form of random distribution of point defects. It could be substitutional when the impurity atom has similar or the similar size as the host atom. For example, here, copper being the impurity to nickel crystalline structure. Yeah, this red circle represents copper. Look, it is smaller than nickel, the size, but however, the more or less almost the same size. So in that case, then it will substitute. It cannot be in the space between the nickel atom crystalline structure because it is just too big. So then it will substitute, it will kick out some of the nickel atom to substitute the place. Yeah. Otherwise, if the impurity is much smaller, the impurity atom is much smaller than the host atom, then they can be interstitial solid solution, like what we have in steel. Steel is made by introducing carbon and in iron. Of course, not only carbon, there are also cobalt and many others inside the iron crystalline structure to strengthen the structure of iron, because iron only usually is soft. But when you put carbon as interstitial to be interstitial solid solution, then it becomes steel, and steel is harder and also difficult. It's not easy to rust, to be oxidized. Solid solution of B in A plus particles of a new phase, usually for a larger amount of B. So the two cases before, only when the impurities are much in smaller amount or concentration compared to the host. But when the B amount is made more larger, then you can have this solid solution of B in a second phase particle with different composition and often different structure. The B will somehow make a new structure with A, like a compound. Yeah, then forming a different phase compared to the surrounding structure. Yeah, it has different composition. Composition means the ratio between the A and B host. Okay, and the structure here also different. The one here inside is, let's say, more like a 1:1 ratio, and also has rectangular, yeah, in 2D shape. Yeah. Well, the other one on the surrounding is more of hexagonal layer. So how come that imperfection in solid can occur, especially for solid solution or alloy? For substitutional solid solution, so substitutional solution is this one, yeah, where the atoms of the impurity usually almost have the same size or shape as the host. This is according to the Hume and rotary rule. Yeah, the first is, as we have mentioned, actually based on the picture, yeah, that the difference in the radius between the host and the impurity is not that large. So the difference in the radius, atomic radius, is less than 15%. And they are closely located in the periodic table. They have proximity in periodic table. For example, they have similar electronegativities. And the crystal structures also are the same for pure metals. Then there is also valency condition. All else being equal, a metal will have a greater tendency to dissolve a metal of higher valency than one of lower valency. So the metal of higher valency becomes the impurity to make that solid solution. This is the application of Hume-Rotary rules in solid solution. Yeah, so for example, we have this element with the atomic, this table, yeah, atomic radius, crystal structure, electronegativity, and valence. Would you predict more aluminum or silver to dissolve in zinc? Anyone can try to answer. Aluminum, this is aluminum, this is silver. Zinc is this one. Aluminum is 0.1431. Silver is 0.1445 radius. And zinc is 0.1332 nanometer. Which one do you think will dissolve more in zinc, silver or aluminum? Chris?
Aluminum.
Aluminium.
Aluminium.
Yes, because
Yes.
the radius is closer to zinc, right, compared to silver. Electronegativity is also closer to zinc. This is 1.5 to 1.6 compared to silver, 1.9 to 1.6. The valency, aluminum has larger valence electron compared to zinc, while silver has less valence electron compared to zinc. Yeah, the host is usually has less valence electron compared to the impurity. Yeah, the rule number 4, all else being equal, a metal will have a greater tendency to dissolve a metal of higher valency than one of lower valency. So aluminum has higher valency compared to zinc. Number 2, more zinc or aluminum in copper. Where is copper? Copper over here. More zinc or aluminum in copper. This is not easy. Which one? Anjali, Andy?
Zinc. Or
Zinc or aluminum? Maybe zinc. I'm not sure. I'm not
quite
sure.
similar, sir.
Huh?
Quite similar.
Quite similar, yeah. Quite similar. Yeah. So let's say zinc has 0.1332 nanometer radius. Copper has 0.1278. Aluminum has more radius difference, yeah, compared to copper compared to zinc to copper, right? 0.1432. So based on the radius only, it seems like zinc will be dissolved easily in copper, yeah, compared to aluminum. However, based on the crystalline structure, aluminum has similar crystal structure with copper. Yeah, and sometimes then maybe aluminum in this case from the crystalline structure should dissolve more compared to zinc. Zinc has HCP. If we compare electronegativity, this one should have similar electronegativities. Aluminum, zinc will have closer electronegativity to copper compared to aluminum, although not that significant. If based on valence, then aluminum has larger valence to copper compared to zinc with copper. Zinc has similar valence electron to copper +2, while aluminum is +3 and copper +2. So yeah, based on valence, so let's try. Based on valence here, so this will be more aluminum, aluminum in copper. Based on this may be zinc in copper. Based on this, aluminum in copper because they have the same crystalline structure. Based on this, zinc in copper because it has closer atomic radius compared to aluminum. So, which you choose? Ezra, Grace, any opinion?
I'll choose aluminium, sir, because the difference between 1.5, the electronegativity between 1.5 and 1.6, it's not really far. So no big difference about that. And because I choose the electronegativity is aluminium, so it's better to choose aluminium.
Yeah, maybe. But in reality, you know the medal brass, right? The brass medal, gold, silver, and then the third one is brass, right? Perunggu, medali perunggu.
Yeah.
Brass is made from what?
Dari perunggu.
No, brass is basically an alloy. Brass is an alloy of copper and zinc. Okay, so zinc is more easily dissolved in copper compared to aluminum.
Okay, sir.
Brass, medali perunggu is not a pure metal. Perunggu is an alloy, combination of metal, which is copper and zinc. Alloy of aluminum in copper, alloy in copper is not that. It's not that common. It's not that common. It can be made, but not that common. Of zinc in copper, if you Google, just Google now. It's easily it can be easily found when you Google it. So it is called brass. It's in this industrial alloy. Okay, so in the FCC copper. Yeah, so here then the answer, the winner will be zinc in copper, not aluminum in copper. Okay, this one is aluminum in zinc. Okay, since time is up, we will discuss again next week for continue.